last class. I had gone ahead and talked about higher order approximations, and in particular, we did certain examples of the higher order approximation also. We tried and we found the Taylor approximation for x to the power 1 by 3. That is the example that I had taken. And then I'd asked you to try this question and to see whether you are able to find the third order Taylor approximation for this equation, which was fx is equal to 1 plus x under root. This is the equation that we were talking about. And you had to find the Taylor approximation around x is equal to 0. So, we just had to use a basic formula of Taylor's approximation, which was this. And now we went ahead and we said that in order to find this Taylor's approximation, we have to find f, what are the things I require? I require f dash x, f double dash x, and f triple dash x. I need these three if I have to go ahead and find the third order Taylor approximation. So that is what we went ahead and we did. In order to find the third order Taylor approximation, let's go ahead and let's find what would be f dash x. So the function that is given to me is fx is equal to 1 by 1 plus x under root. So f dash x will be, see, this is 1 plus x to the power minus half. Okay. So f dash x is going to be minus half 1 plus x to the power minus half minus 1, which will be minus half 1 plus x to the power minus 3 by 2. Then we went ahead and we found out what will be f double dash x. And we found that f double dash x will be minus half into minus 3 by 2, 1 plus x to the power minus 3 by 2 minus 1. So this will be plus 3 by 4, 1 plus x to the power minus 5 by 2. Finally, you can go ahead and you can find the Taylor, you can find f triple dash x. So f triple dash x will be 3 by 4 into minus 5 by 2 into 1 plus x to the power minus 5 by 2 minus 1. And if you solve this, you are going to get minus 15 by 8, 1 plus x to the power minus 7 by 2. Now, once you have gone ahead and you have found out what is going to be fx, f dash x, f triple dash x, f double dash x, etc. The next thing that you have to go ahead and do is put x is equal to 0. That is what we did. So here, if I will put the value of x as 0, because this is what it is asking me to do, to find the approximation around x is equal to 0, what do I really get? I'm going to go ahead and I'm going to get here 1. I'm going to get here minus half because this will become 1. 1 to the power anything is 1. I'll get 3 by 4 and I'll get minus 15 by 8. So I have been able to find the derivative of the function and I have been able to find these derivatives here. These are the values that I have got. Now just find the Taylor's approximation, put it in the formula and see if you're able to solve it further. So if you put it in the formula, you will get fx is approximately equal to fa plus 1 by 1 factorial f dash a x minus a plus 1 by 2 factorial f double dash a x minus a whole square plus 1 by 3 factorial f triple dash a x minus a whole cube. A is 0, remember. So the value of the function at 1 is 1 by root 2. at 0 is 1. I have to put it at 0. So this gives me 1. So this is approximately equal to 1 plus 1. F dash A gave me a value of minus half. So I'm going to get minus half and then x minus 0 plus, what is 2 factorial? 2. F double dash A, what is the value that you got? 3 by 4. So into 3 by 4, x square. What is 3 factorial? 3 into 2, 6. What is F triple dash A? We have already found out that minus 15 by 8 into x cube. So it becomes approximately equal to 1 minus x by 2 plus 3 by 8 x square minus, so this is 3 2s and 3 5s, 5 by 16 x cube. So this is how we go ahead and we do Taylor's approximation. You can try with the different Taylor approximation values and see if you're able to solve this. Now, today I want to go ahead and I want to introduce, you can try this also. You can try Taylor's approximation for e to the power x. This is very, very important in particular. And why is this important really? Because here in this case, we know one property of the function, that when I find f dash x, f double dash x, f triple dash x, how many ever times you differentiate the function, the differentiation of e to the power x will remain e to the power x. So this is one good property of this function. And then if you have to find near x equal to 0, about x is equal to 0, so your a becomes 0. So f dash at 0 and all these values at 0 basically give you e to the power 0, which is 1. So you get the same answer, which is 1 everywhere. So, in my Taylor's approximation, then this is very useful to me. What is my Taylor's approximation? That the function is approximately equal to the value of the function at a plus f dash a x minus a plus 1 by 2 factorial f double dash a x minus a whole square plus 1 by 3 factorial x minus a whole cube and so on till n. But the value of the function at 0 is 1. The value of the differentiation is also 1. This is x minus 0 plus 1 by 2 factorial. Double differentiation is also 1. X square plus 1 by 3 factorial x cube and so on. So ideally, this is a very, very, very important equation that I am going to go ahead and use a lot of times. I'm directly going to say using Taylor's approximation. So this is very important, where you will simply say that Ex is approximately equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on till x to the power n by n factorial. Very important, very, very important derivation. Now, here's the thing. See, what we did till now always gave us Taylor's approximation, that this function is approximately equal to this value. But if I want to change this approximation by an equal to sign, then what can I say? I can say this function is equal to this plus minus some value. Then, just see this. We had got E, when I did a linear approximation, I'll go back to that lecture once. So when we did linear approximation and we were to find, the cube root of 1.03, its linear approximation came as 1.01. And when we found its quadratic approximation, then that approximately came equal to 1.0099. And when we actually find in calculator, then this comes approximately equal to 1.0099 with some other decimals also. So ideally, as we do go from linear to quadratic to cubic approximations by using this formula of Taylor's approximation, we keep on going to a closer value of the actuals. What the actual cube root of 1.03 is. We go closer and closer to its value, to its actual is equal to value. But this linear approximation is also very close to this value, but it is plus minus something, very small number. So maybe when I, if I find out the difference between 1.01 and 1.0099, I'm going to get 0.0001. So only this is the remainder between these two things, right? So this has been just a little more than the actual value, and that little more is very less. So if I have to go ahead and replace this approximation sign with an equal to sign, I am saying whatever value you get after approximation, just plus minus something will give you the actual value of the function. This plus minus something, this is called the remainder.